Thank you very much for having me today. And thank you very much, JetBrains, for hosting this event on this lovely location. My name is Dominik. Today I want to give an introduction to CAF. And it really is going to be an introduction, so I'm not going to be, I won't have the time to go deep into the framework. So I will touch on a lot of things. I will cover the basics. And after that, I will mostly show off some of selected features, but I won't even have the time to talk about everything that is in CAF. So what is CAF in the first place? Well, CAF is an acronym that stands for C++ Actor Framework. It's a native C++ engine to build concurrent and distributed applications. And it seamlessly integrates web technologies, for example, HTTP, WebSocket, and so on. And we will later have 2 examples how CAF allows you to write a REST interface, for example, with actors in the background. CAF is open source. It's licensed under the BSD license, so you can use it for any project you want, even commercially. And it was incubated back in 2011 at the HAW Hamburg, which is a university for applied sciences. So our self-understanding is that we don't want to just advance the theoretical science, but that we want to take something from the science and put it into practice. And this is how basically CAF came to be. We wanted to have a framework that's not just some academic toy, but really that helps people build software to scale their applications. And back then it was a research topic. Today it's used by many companies. For example, in the trading world, in the visual effects industry, in cybersecurity. So there's a whole lot of range of applications that we see, which basically tells us that what we wanted to build was the right thing. So we wanted to have something that has a wide range of applications. If you are building single core software, or if you're run on the cloud, CAF will have some tool to help you to build what you want to do. This talk is going to be structured in 3 parts. Part 1 is basically a crash course on what are actors, what is message passing and flow processing in CAF. And part 2 is going to be basically a selected list of features that hopefully whet your appetite. And then part 3 is just a couple of pointers where to start if you're interested in the framework. So let's start with actors and message passing. I already used this term like quite a lot, so let's define actors. These blue boxes are actors. These arrows are sent to relationships, so actors message to each other. And these green boxes are pending messages. So each actor has a mailbox, and this is just a visualization of there are some inputs to the actor that it processes one by one. And these arrows basically allow you to understand who is communicating with whom. The term dates back to a 1973 paper at MIT, written by Hewitt, Bishop, and Steiger. So it's actually a very old idea. And in case you wonder, yes, actor really means actor on a stage. The metaphor is that you have a lot of these actors, each acting according to a script, and all together form your system or your play, if you take the metaphor to real world. The interesting bit about actors is that they are distributed by design because they don't share state. You can basically deploy them wherever you want. And you have a programming model that works for concurrency and distribution, which I think is very unique to this particular model. And not necessarily from the paper, but in practice, you usually have a very hierarchical system where you have some actors at the bottom doing the actual work. And then you have basically hierarchies of actors where you have actors managing other actors. And then you have this hierarchy to allow you to do very nice error handling. And of course, divide and conquer. So you have something coming into your system, you break it down into smaller parts, and then you spread it out to various actors. And the runtime system, in this case CAF, will just use whatever cores you have available. So if you have 100 actors and they all have messages to process, and you have 100 cores, then they all run in parallel. And to give a bit more information about the model, actors are inherently event-based. So you can think of messages as events. A message comes in, and then in response, the actor does something. And in the actor models, this something is one of three things, or any of them. You can send more messages. You can spawn more actors. So your set of actors is not static. In fact, if you look at applications, it's very common that you spawn actors dynamically, and then they do whatever they have to do, and then they shut down again. And actors are very cheap. In Kef, you are talking about a couple hundred bytes to create an actor. So it's not like spinning up a thread where you have to do some several kilobytes of RAM or something. It's very lightweight objects, and you can have a lot of them. And of course, actors can change their behavior. And behavior in the actor model basically means your set of message handlers. So a message comes in, and your behavior defines how you are going to respond, and you can change this dynamically. If you think of an actor, and even back in the original paper, there is basically three things to an actor: processing, communications, and storage. Processing is basically just some means to run your code. And you can think of actors as state machines, and then you can basically follow this flow. You start the actor, you wait for the next event message, then you run your code, whatever you want to do, and then you are either done, and then the actor shuts down, or you are not done, and then you wait for the next input. And storage is just a fancy term to mean state. You can have explicit state, like member variables, integer strings, custom objects, whatever you have. And in your message handler, if you are using Lambda expressions, there's also implicit state that you can have. Here in this Lambda expression, we are capturing the this pointer. And in C++, you can basically bind whatever is in the context. And your Lambda capture basically also is some kind of state. But that's just a detail. Communications is the one bit that sticks out of the actor. So this blue circle around the actor is basically whatever stays, whatever is inside stays inside. You cannot access something in an actor from the outside. The only thing you can touch is the mailbox. And this is why this email box reaches out of the actor, because this is the part where the actor can actually receive something from the outside world. And then you have an actor handle, and this gives you write-only access to the mailbox. So you can only put something into the queue, but you cannot take a message away from an actor. And you can also use this handle to observe the lifetime of an actor. And the terms are links and monitors, and we will discuss both of them later. But for now, I want to show you how message passing works in Kef. There are two flavors. The first flavor is fire and forget. So this is just sending a message, and I don't care what happens. And if you start a message in Kef, you always write self, which is basically the actor, the pointer to the actor itself, very much like the this pointer points to the object in object-oriented programming. We have the self pointer pointing to the actor. And you always start with mail, and these ... are the values that you want to send. And then you have your email that you want to send, mail that you want to send, and you can call .send, and that's going to send it as a fire forget message. Or you can use .request, and then you have a request response style. And if you are doing request response, you are not going to process the response just like any other message, but you have to give a handler specifically for this response message. So there's this .then at the end, and usually you pass in a Lambda expression to process the response message that's going to come. And this will allow you to unambiguously match the message that you send to the message that you have received. And if you do the first pattern and the actor sends you something back, you will process it like any other message because you don't know what caused it. Okay, let's write our first actor. And it's actually just as easy as writing a function. And in this case, we have Kef behavior. I already told you a behavior is basically just a set of message handlers. And in our case, the message handler is just waiting for a string. So we are passing one lambda expression to construct the behavior. And then we print something if the actor is initialized, and we print whatever string we have received. And the self pointer is actually optional. If you don't care about the self pointer, you don't have to take it as a parameter. You can just use no argument for the function. And whatever lambda expressions you pass to the behavior are going to be used to process messages that are incoming. And creating a new actor is just using the actor system. This is like your hub for everything you do in Kef. You have your Kef actor system, and the canonical way is that you write a Kef main function. You can also return an integer if you want to, but you can also declare it void. And then you always get the actor system as a reference, and then you can spawn actors from the system. And in this case, we are calling sys.spawn and just give it the function. And this will create the actor for us. It will start the actor, and then we can send messages to it. And we send a message from main to it. This is a free function, anon mail, anon for anonymous. So there's no sender information. We are just sending a message without any way for the receiver to respond to. And in this case, we send the string hello to my actor, and this will then call the message handler and will print my actor receive double point, colon, and hello. So that's a nice approach if you have actors that are very simple, but usually you will have to manage some state with actors. And the way you do this in Kef is you just write an ordinary class or struct, and you then have your regular member functions and member variables and all of the things you want to have. And in this case, we have some value. This actor represents a cell, so it has a value that you can set by sending it a put message, and you can get the value back with a get message. And these atoms are actually just empty structs. They are basically just metadata that you can tag to a message to give the message more meaning. So if I would just send an integer to some actor, I wouldn't know what sending this integer means. And by putting this put atom in front, I know, okay, I want to have this thing, the semantic of putting a value to the cell, and I can use the get atom to mean get your value from the cell. And the only thing I have to do different from before is that I don't just give it a class and I don't just give it the object, because this state is going to live inside the actor. So I don't want to give the spawn function an instance of this thing. I want the actor to construct this. And what I use is this actor from state utility, and it's a template. I just give it some class that I have written. And the only thing that cell state has to provide is a make behavior member function. That's all. So you can write any class you want, whatever state you want to have, and then just put a make behavior function in there, and you have basically just written an actor. And then we can, of course, use this thing. This time we are going to write the actor again as a function, and we receive a second parameter, which is a handle to the cell. Kef actor is just a handle type. And then we can send messages. So here we say, I send a put atom with 1, and then 2, and then 3. And eventually I want to ask this thing, hey, what's your current value? And then I send it a get atom as a request. And the handler that I pass to then takes the response value. And the actor that the cell actor is going to send the value back to us. And this will just send 3 messages as fire and forget, and then send a request and wait for the response. And in our main again, we can spawn our cell, and then we can spawn our client. And whatever we pass as extra arguments after the function goes to the function as additional parameters. And we can do the same with classes. So if you have a state class, then whatever additional arguments you pass to spawn are going to be constructor arguments for your state. All right, at this point, you might be thinking to yourself, what happens if I send a string to this selector? Because I send anything, right? And the answer is you get an error at runtime. And maybe you're thinking, but I'm doing C++. I want to have static type checking. Okay, we can make it statically type checked. And you do this by writing this sort of trait class. The only thing you have to do is have a signatures member, which is a type list. And then you are defining a messaging interface. So every entry in this type list is a signature that you want to allow. And the format is that you always have to wrap the result in calf result. Even if it's void, you write calf result void. You can have multiple return values. So you can write calf result int double string, and then you have 3 return parameters. And in this case, we define the interface for our cell. So there is a get atom that returns an integer, and there is a put atom that takes an additional integer as argument, and it returns nothing. So it's just void. And then you can define an alias. So there's this typed actor, which is a typed version of the actor handle that I showed you earlier. And if you are using a typed actor, then the compiler can check both sides of the equation. So it will check that the selector implements the proper interface. And if you want to send something to the selector, it will say, this is not a type that is allowed here. And the selector basically looks almost identical to before. The only thing that has changed is that we no longer return just calf behavior from the make behavior function, but we take the behavior type from this type alias. And just by doing that, the compiler will check that, first of all, that you actually accept everything that is promised in the interface. And if you have typing errors, then the compiler will give you an error. And it will say something like, the handler at index 0 is invalid, or something like this. And the client also, again, looks almost identical. The only difference here is that the cell parameter no longer is just a calf vector, it's a selector now. And down here, we have used auto. So the code actually doesn't change at all. But if you are calling spawn, then calf will look at what you are going to spawn and give you the appropriate handle. So in this case, spawn no longer returns just a calf vector. It will actually return a selector. And if you try to assign it to a calf vector, you will get a type error, because the calf vector is dynamically typed, and this is statically typed, and then the compiler will tell you this is something allowed. Okay, this was the crash course on message passing. I hope everyone is still following. Next, we are going to talk about monitoring and linking. And monitoring and linking is how you do error handling in calf. And this is a very explicit style of doing messages, very explicit style of doing errors. And the errors are propagated via messages, of course, because everything is a message in the actor model. The difference between monitoring and linking: monitoring is unidirectional. So you observe something else, but that something else doesn't care about you. The classical example is you have a client and you want to know if the server is still there, but the server doesn't care if the client is still available or not. It just does its thing. And linking basically is a much stronger version where you couple the lifetime of these both things together. And a classical example is if you have some supervisor that manages a set of workers, you want to have the supervisor know if a worker fails, and you also want the workers to know if the supervisor is no longer there, because if no one is giving them tasks, then they should just shut down. And in this case, both sides of the equation have to know if the other party is still alive, and then you are using a link. In terms of how you would write this in source code, here we have a very simple client. It just takes a handle to some server that it has to talk to. and you just say self-monitor, give it the handle of the actor that you want to observe, and give it some callback what needs to happen if this actor goes down. And the callback takes a CAF error, which tells you what happened. If nothing happened, so if the error is default constructed, then it's not actually an error. It just means that the other actor has decided that everything is fine and it just shut down as regular part of its execution. But if there is some error, then you can do whatever you want with it. In this case, of course, only the client will get a notification. So the server doesn't care if this client goes down. And here in this callback, we are just calling quit, and quit terminates the actor. So it just tells CAF, this actor is done, please do it, do away with it. Okay, that's monitoring, straightforward. Linking is a bit more involved. And here I have an example where you have a server that manages some amount of workers. So it has a list of workers that it has to maintain. And there's an index. Maybe it does round robin of tasks or whatever. And then we have a constructor where we receive the self pointer from CAF. Again, the last state that I showed you, the cell, didn't care about the self pointer. So you didn't have to write a constructor at all. You can have a constructor, and if you write one, the first parameter to your constructor can be the self pointer, and then you can just store it as a member. And your make behavior function would be look something like this. You spin up some amount of workers. So here we just spawn 3 workers. And by using this linked tag for spawn, you tell CAF, please spawn this actor, and then immediately call link to. So it's not different from doing it by hand. It's basically just syntax sugar. And what it does is it just spawns an actor, calls link to, and then puts it to the vector. And this time, this is bidirectional. So if this server goes down, the walker receives an exit message. And if the walker goes down, we receive an exit message for the actor. And an exit message is a built-in type in CAF that you can handle in your regular behavior if you want to. So the default thing in CAF is if you don't provide a handler for exit message, the default is that CAF looks at the exit message, and if the other actor failed due to some error, you shut down as well. And this will allow you to build systems like here in this example, we have the server and you have the workers that are managed by the server. And you know that this is basically a subsystem where all of the actors are alive, or if the server fails, then all of the workers will terminate as well. So you don't have to worry about partial errors in your system where some workers are still thinking everything is fine and they just sit there and no longer actually have someone talking to them. And doing it this way with linking, you just know, okay, if the server fails for some reason, everything will go away, and you can have a supervisor on top that maybe restarts the server, or you can just shut down your application or whatever is appropriate. Okay, that's the crash course on error handling. Next is the crash course on data flows in C++, or rather data flows in CAF. The obvious question is, okay, we already have ranges. Why do we need something else? Ranges are basically sequences, a sequence of items that can be produced on demand. So it's usually lazy sequences or some kind of container where the values are coming from. So something that you can either reach into memory and get, or something that you can compute. And flows, which in CAF very much uses a ReactiveX style API. So if you have ever used something like RxJava or RxJS, these things should be very familiar. If you never heard of anything like this, don't worry, I will cover the basics of it. And the mental model to have is that flows in this world are sequences that are emitted over time. So it's not something that you can just compute on your own, for example, this could be a live feed, like a Twitter feed, or some asynchronous event, some thing on the internet producing something that you will want to consume. Or it actually can be messages. So you can have some kind of messages sent to you via WebSocket, for example, and then you can hook these things into a flow. And these things happen over time. So it's not just something that you can iterate over, but it's something you have to wait for. And because of that, the API is very much geared towards reactive processing. So it's not the model of I have this range and I iterate over it, but it's this model of I have items popping up over time and I respond to whatever comes. And there's also built-in back pressure. That means, say you have a source reading from Twitter or whatever and produces tons of data, and you have your source somewhere over it in some corner. And if that thing that consumes the values isn't fast enough to keep up, then the source will eventually be notified. And either it slows down if it can, or if you have to respond to live data, then you can decide what to do with a slow client. You can just drop it, or you can say, okay, the data I'm receiving, for example, is periodic data, something like a sensor that I pull regularly, and then I can just drop the oldest value and just push into the queue and just keep the new values, because at the end of the day, the client is only caring about the most recent thing anyway. All right, a bit of vocabulary. The building blocks for this Flow API. If you ever heard of ReactiveX, this should be very familiar. There is this observable, which represents our sequence of items. And in Kef, this sequence or this observable is actor local. So the actor itself is basically the environment for the observable. And then there's an observer, which consumes item from the observable via a subscription. And a subscription is basically just a piece of code that manages data flow from some observable to some observer. And then there are operators. Operators are basically modifying an observable and creating a new one. So if you call filter, map, reduce, whatever, you have an input observable that you modify, and out comes a new observable. And in Kef, there are two more things. There's a publisher, which is an asynchronous version of an observable. So this is something that you can pass around in your process, which is safe to consume from other actors or other threads even. And there are streams, and streams built on top of observables and allow you to pass this sequence of events around in your distributed system. So this is something, if you generate a stream on one actor, you can actually send the stream in a message to another actor and tell it, hey, here is the stream. If you're interested, consume this thing. And in terms of object interaction or protocol between these things, so on the right hand, there are observable, observer, and subscriptions. And the first thing that usually happens is that the user calls subscribe on the observable. It passes in the observer as an argument. And the observable creates a subscription to manage the state for this particular observer. And then it will pass the subscription to the observer via onSubscribe. And then the observer can request items. So it can say, I request 100 items from you. And this allows the observable to send 100 things to the observer. And it does deliver things by calling onNext on the observable. That's just to understand how the internal machinery works. If you are actually working with flows, you usually don't write observers, and you usually don't have to write subscriptions, but you can. So you can write your own observables in Kef if you really want to. This is where to look at. But if you just care about some flow, you just use the Flow API. And in Kef, you start by saying self make observable. This basically gives you a factory. And just to fit on a slide, we keep it simple. So there's an IOTA operator that says, give me an infinite sequence starting with whatever you pass in. So we can give it 1, and this will create the infinite sequence 1, 2, 3, 4, 5, and so on. And then we throw everything away except even numbers. And then we can say, okay, actually, I just want the first 5 values. I don't care about the rest. And then you can map things and say, okay, I double each value that comes along. And each time you're basically creating a new observable, sort of. If you're done with this thing, you can say for each. And for each, we'll create an observer for you that basically runs this lambda on each invocation of onNext. So here we just print out everything. And actually, Kev does operator fusion. So this iota filter take map will all end up in a single observable. So it will try to minimize the amount of heap allocations and state and all of the stuff that's going to happen. It tries to be efficient. So that's just a flow that runs on one actor, which is not terribly interesting. Let's make it a bit more interesting by embedding messages. So we have the same flow from before, iota filter take, but this time we want to be lazy and we don't want to make the mapping ourselves. We want to have an actor that does the addition for us. It's not a good use of messages because sending this message is more expensive than doing the calculation, but for the sake of an example, we can use concatmap. Concatmap basically takes a function that returns an observable, and then it will subscribe to each observable one after another. So it will basically, for this sequence, the first value will be 2. Then it will call the function with 2. And in the callback, we send a message to our worker and say, please add x to x. And this is a request. And the magic sauce here is that you can turn a request into an observable. And by doing this, you no longer need to give a .then, because the response is no longer handled by a message handler, but it will basically be an observable that emits exactly one value or an error in case nothing happens or something bad happens. And that's basically all you have to do to embed actor messages into flows. And then you can, again, do for each, and this whole thing starts. Because up until this for each call, everything is basically just a blueprint. And only if we call for each, then the machinery starts. All right, publishers. As I said, you cannot take an observable and give it to another actor because the observable belongs to the actor. And remember, nothing is allowed to leave outside of the actor, except if it's a publisher. Then it's okay. And here we have our iota take again. And in the very end, we just call to publisher. And this will give you a asynchronous version of an observable that you can give to another actor. And here we just spawn a new actor in place. We capture the items as lambda in the lambda, and then the new actor, which is the source sync, SNK, can just say items.observe on, then pass in its self pointer, and this will turn the publisher back to an observable, and then you can do everything that you want with it. And under the hood, just as a mental model how this thing actually works, under the hood we have our actor A, which has this iota take 5, and then it feeds into an SPSC buffer, which stands for single producer, single consumer. So this basically connects one actor to another, and the data travels through an asynchronous buffer in between. And this allows us to transfer data very efficiently in a single process. But of course, this won't help you if you want to this won't help you if actor B lives on another thread, on another process, or even on another machine, because you can only have a asynchronous queue in the same process. So this is where streams come in. If you do stream processing, then Kev will do batching, because if you send each item in a flow individually, you will incur a lot of overhead. So Kev will try to bundle things into one little batch to minimize the messaging overhead. And in the API, you need, or you don't need to, but usually what you do is you have 4 constants, the batch size, which tells Kev how many items should fit into one batch. And there's a max batch delay, because if you do batching, you are introducing delay. And if this is some live source from events that you get, you want to send off data at some point. So if your batch only has 8 items in it, you still want to send it eventually if nothing new comes along. And this is basically timeout that tells Kev, hey, I don't care how many items are in the batch. After 50 milliseconds, send it anyway. And then you can have a maximum buffer. This is for the receiver, which tells Kev how many items you want to buffer at the receiver. And this threshold is just a tuning parameter to basically configure how many demand messages you are sending upstream. That's a bit theoretical, so let's look at an example again. Here we have some source. We have a message handler that waits for a get. And if we receive the get, we create an observable. We have our IOTA take 5 again. This time we turn it into a stream. So we don't call the toPublisher, but we call toStream. And this turns something that is local, the local observable, into a stream. And the stream is like a first-class citizen in CAF that you can pass around. So this is message passing. So we receive a get at a message, and we send back a stream handle. And the other actor can then subscribe to the stream and even can share this handle with other actors that can also subscribe to the same stream again. And on the consumer side, on the sync side, we write an actor again. We have the source as a parameter, and then we ask the source, hey, please get me your stream. Then we do a request, wait for the response, which is a stream handle, and we turn this thing back into an observable by calling self-observe as again. And a Kev stream is type erased by default. You can also get type versions of this thing, and then you don't have to give the int to observe as, but this is like the dynamic thing, very much like you've seen before with actor and typed actor. The same exists for streams. There is a stream and there is a type stream. And the difference is that for one, you just have to be a bit more verbose, have to write more boilerplate code. So as long as you know I only have this interaction between 1 or 2 actors, you can just use the dynamically typed version and save yourself some typing. And under the hood, it's a bit different this time. We have the same actor A and actor B again, with IOTA and take 5 on actor E, and actor B does the mapping and the for each. But this time there's actually message passing between these actors going on. And the first pair of messages is the handshake. So actor B tells, hey, I want to open this stream from you. And then if the stream is still available, then it responds with an egg. And then after the handshake is complete, then there are pairs of demand and batch messages. So actor B tells, hey, I'm ready for like 10, 50, 100 new items, whatever. And then actor A can send more batches. All right. That's the crash course on streams and flows. And I want to scratch the surface on a couple more Kev features. Again, the idea of this talk is not to give you a very deep understanding of Kev, but just to tell you that this thing exists, how the primitives work, message passing actors and flows. And what I do in part 2 now is I highlight a handful of features in Kev that are good to know about if you're interested in the framework, and I hope that are also interesting to know. All right. The first thing we need to talk about is type inspection, because in Kev, everything you send has to be serializable. This is a consequence of actors can live anywhere, and anywhere can mean I have to send something across the network. So I have to be able to serialize things. And C++ still has no built-in way of reflection. So we have to do something in Kev. And what we did is we have an inspection to name specific language, which allows Kev to basically deconstruct any C++ type that you throw at it. And you have to do a bit of manual setup to get this working, but it's not that much. But once a type is inspectable, then it is serializable. It can use in configuration files and send across the network and all of this stuff. And to give you one very quick example, let's say we have this point3d that we want to use in messages. It has XYZ. And all I have to do to tell Kef how to serialize this thing is to write an inspect function. This is just a free function. It takes some inspector as the first parameter. And this is a template parameter because Kef has multiple different inspectors. Some inspectors generate JSON, some inspectors generate just a string if you want to print something to the console. Others generate binary data. So it's a template parameter. And then the second parameter is your point3d. And the DSL is very straightforward in the sense that you call on the inspector, you say .object. With this, you say, okay, I'm starting a new object here. And then you call .fields, which tells Kef, okay, in this object, there is a field X, Y, and Z. And then you give it pointers to the members. And then Kef knows exactly how to serialize this thing to and from JSON, or how to send this across the network, or whatever you want to do. Of course, there's a lot more to it. If you're interested in this, just read the manual. And in the manual, it will also go into much more detail about how the type system for the inspection API works and all of the stuff. Okay, configuration API. If you have an application, you very, very rarely can do without user interaction. Usually you have to have some kind of user-provided configuration. A server you need to connect to, a file you have to read, whatever. And Kef can do that for you. It can parse command line arguments for you. It can parse config files for you. And the customization point that we have in Kef is this class called actor-system-config, which is responsible for all of this stuff. And you can basically inherit from actor-system-config and customize it. And you can also read the configuration in your application. And the two functions for this are getAs and getOr, which we will see in our next example. So here we have a class config, very creatively named, and it just inherits from actor-system-config. And in the constructor, you can add additional parameters that you want to be able to configure. And the syntax being used here, this port comma p, this is the long name, and after the comma come short names. So on the command line, you can say application -p, or you can say -port. Same thing, it's just more convenient for the user. And the last thing is the environment name. You can override it if you want to. By default, Kef will look for an environment variable that is named for the long name, all uppercase. So for example, max connections become max_connections, all uppercase. And this allows you to basically use command line arguments, configuration files, or environment variables, whatever is most convenient in your setup. And you can also have groups. This first group was added to global, which is basically the global namespace. So everything that you add to the global namespace will be on the top level. If you write a configuration file, you just say port = 5, for example. If you give it another name, in this case TLS, then in your configuration file, you will have a section TLS, and then the key file and the certificate file are in the scope of this TLS section. And in the application, you can use our Kef main function again. And this time you just give it a second argument. And just by giving it a second argument, Kef will look at your type signature and see, okay, you want me to construct a config object. By default, it will just create an actor-system-config, so the default type. But just by using config as second parameter, Kef will construct your config object instead. And then you can read the configuration programmatically. You can use getOr if you have defaults. So in this case, we have a port, and we also have a default port, for example, 8080. And getOr will look at the configuration, look for this port parameter, and if the user didn't specify any, it will return the default port to you. Or you can use getAs, and you can use getAs if there is no sensible default or if you don't want to set one. So for example, if you want to spawn an HTTPS server, you have to have a key file and you have to have a certificate, and there is no default that I can use. So I use getAs instead, and getAs has to know the type. getOr can just look at the default that you pass in and know, okay, you want an UN16 or whatever. getAs doesn't have this information, so you have to give it a type, and then it will return an expected string in this case, which is an error or the actual value. And if it's an error, then CAF will tell you what went wrong. It could be that there is no such key or the conversion failed, because you can actually use any type in here. You can also use your point3d from before, and then CAF will try to convert whatever is in the configuration to a point3d. And if this conversion fails, it will tell you, I couldn't convert this thing to a point3d. Okay, next thing, distribution. I mentioned distribution a couple of times. You can think of the actor system spanning multiple nodes. So in this case, we have multiple actors that have connections to each other, and they really usually don't care about the nodes that they are running on. And this is because messaging is network transparent. So on the programming side, you just receive an actor or a typed actor, and you can send messages to it. But in reality, this thing can live anywhere. So remote actors use transparent proxy objects so that CAF can basically give you the same handle for a local actor and for a remote actor. And all of the magic is happening underneath. And you can even spawn actors remotely. So if you have multiple nodes in your system, then these nodes have IDs. And you can also, in your application, explicitly ask for this ID and use it for spawning, or you can monitor an entire node. We have already seen monitor for actors. You can also say, okay, I want to receive notification if node B, for example, goes down, because then I want to do something. Maybe I want to raise some alert, whatever you want to do in your application. And if you want to connect to remote actors, you have two ways in CAF at the moment. The first option is to have a rendezvous process with a dedicated port. So on the server side, you have this publish function, and this allows you to open up one port where you want to expose one particular actor, which is most of the time all you need, because usually you only have one, maybe two actors that you want to expose over the network. And once you have an actor handle to the other process, of course, messages can reach out to different actors on the other machine. And on the client side, you just call remote actor with your host and your port, and you get back an actor handle that you can use just like you could use a regular actor handle. The second option is to use the registry in CAF. There's a registry in the actor system that you can use, where you can basically assign a specific name to actors that should be available to other actors just via name lookup. And then you can say the middleman, which is the component in CAF that manages all of the network stuff for you. You can just say, open up this port and wait for incoming connections. And on the client side, you can use connect instead of remote actor. And this will return a node ID. And this node ID can be used for remote spawning, or you can say remote lookup on the middleman again. And then you just give it the name that you want to look up on the other machine and the node ID where to look at. And remote spawning, if you want to register a type actor, if you want to register an actor type, then that allows you to scale your application dynamically. For example, you can have some supervisor sitting in some part of your system that just waits for machines to come up, and then they register themselves at the supervisor, and then the supervisor can start workers on all of the machines available to your system, which allows you to very easily just throw more hardware at your application if there is too much demand for it at the moment. And the way you do it in CAF is there is this function add actor type. This is on the actor system configuration. So you can, again, write your own config class. You can just, on the configuration, register all of the actor types that you want to expose or to make available for remote spawn. And then after that, you can use remote spawn on the middleman again, and you give it the name, the node ID, and whatever parameters you need to pass. All right. I promised HTTP in the beginning, so here we are. The API in CAF is very declarative. There is this entry point CAFnet HTTP ref, and it takes the system that you want to run your HTTP server on. And you also can configure SSL. You can give it additional parameters like how many connections it should accept. And the way you customize your HTTP server is by adding routes. If you have used HTTP libraries in C++, then this should be very familiar. For example, Qt has a very similar thing where you just have your HTTP server, you add routes, and then you start it up. And the way this would look like in CAF, let's say we have some key values director. We don't really care about the implementation here. It's just something that has some key value store. Maybe it writes to a database, whatever. And we want to implement a REST interface for it. Then what we want to do is, in our application, we use this HTTP with as entry port into the DSL. And then we can configure TLS. And we can configure it in a very declarative way. So key file and cert file, if you remember a couple slides back, we had this read from the configuration. So these are expected strings. So we check if there is a value in key file, and if there is a value in cert file, then we want to enable TLS. And then you basically get back an expected, and you can chain additional things you want to do with your SSL context. If you are familiar with, I believe, C++23 expected also has these and then operators. This is just a C++ version, C++17 version of the same thing in CAF, because we don't enforce C++23 at the moment. But the idea is the same. Once you have your SSL context enabled, you want to say mplace server, and you want to have at least TLS 1.2. And then you give it your private key file, you give it your certificate file. And after that, if this setup completes, you will have HTTPS. If the key file or the certificate file was not available, then this will just run HTTP. And of course, you can do a different setup if you want to enforce HTTPS, but this is a very convenient way to allow the user to provide these things if he wants to use HTTPS, and otherwise just fall back to HTTP. Then you tell it what port you want to run at. We can limit the maximum amount of connections. We can limit the maximum request size. And we can also tell our server, hey, please monitor this actor for us. And what this means is, if this key value store actor goes down, this server will go away. So there's no point in providing a REST interface for an actor that no longer exists. So it's very convenient in CAF to just say, monitor this actor and go away if this actor goes away. And then we can start adding routes to our HTTP server. The syntax is we give the HTTP path, in this case, these angle bracket arg becomes arguments to the function. And you can see the lambda expression has the HTTP responder. This is always the first parameter. And then you can pass any number of additional parameters, and they are taken from the URL that the user has passed in. And we restrict this path to HTTP GET, so only GET requests will end here. And in this case, we want to talk to the key value store actor. So what we do here is we cannot produce a response immediately, so we turn this responder into a promise. And this allows us to basically delay the response to this incoming HTTP request. And then we can do messaging in the meantime. So here we again self-mail. We send a GET with the key to the actor. We wait up to 2 seconds for a response. And then if we receive a string, we send it back to the client. So we fulfill our promise. We call promise respond. We say HTTP OK status, give it text plain, and whatever the actor has returned to us. Or in case of an error, and the second parameter to .then is something that you haven't seen before because it's optional. Usually you can omit it and it will just terminate the actor if something happened. But in this case, we want to do something with the error because we want to communicate this back to the user. And so here we look at the error code. If the actor responded with no such key, then we will be nice and we say, this is not found, there's no such key, do something else. And otherwise, we just say, internal server error, something happened, please try again later. And again, the second handler here is optional, but if you do something like this, where you want to do something with the error, it's very convenient. And of course, you can also do post. So here we add a route that only is valid for post. And again, we have the key as taken from the URL, but this time we care about the payload. And if you call payload on the responder, you get a span of bytes. And then we have just a couple of convenience functions. We can ask or iterate the bytes and see if this is actually ASCII. If it's not, we say, this is not ASCII, please go away, do something else. And here you can see the API for responding immediately. So we call just respond on the responder, and this will send something back immediately. So you don't have to use a promise. You can just send something if you can have the answer right away. But if this is a valid input, then again we send it to the actor, and it's basically the same as before. Okay, if you have declared everything in your server, you can just start the thing by calling .start, and then everything it will set in motion. And if you remember, this whole thing actually returned something. It returned a handle to the server, and this is an expected disposable. And it will be an error if something happened. For example, the port is not available, or if you have some other error, then you can print it to the user. And this print line thing, just a side note, I've already used it on actors. In Kef, this print line function exists on actors and on the actor system, and it will make sure that there is no interleaved output, even if you do coloring. All right. And if you're done with the server, you can just say server dispose, and the whole thing will go away for you. WebSocket is also available in Kef. You have two options, actually. You can just use a regular HTTP server, and there's a predefined helper that you can use to declare a route where you switch from HTTP to WebSocket. And this is just called switch protocol. So you do kefnet WebSocket switch protocol, and you can pass that to a route. And then you can basically have an HTTP server that has a REST interface, but also provides an endpoint for WebSocket. Or option 2, if you don't want to have a regular HTTP, there's also like a dedicated WebSocket server, which we also have a small example for. We again start our server. It's just a different namespace again. We call the with function, which is the entry point. Then we do the same thing as before. It's same as for HTTP. We can declare this context. If this context actually creates an SSL context, then you will have WebSocket with TLS. Otherwise, it's plain. And then again, port, max connections, all of the stuff. This is something new. And this is an on-request handler that allows you to reject incoming WebSocket handshakes. So WebSocket operates in a way that it uses HTTP for the initial handshake. And if this handshake succeeds, then you have a bidirectional connection between the two things. And this allows you to look at header fields, look at the path, or even additional arguments that you can use, and make a decision right away if you want to reject an incoming connection. For example, if the client failed to send some header field that you expect, or didn't provide a path that you expect, or whatever. And then there's this start again, but this time you have to pass in a callback. And the callback has these events thing. And WebSockets are basically a flow of frames in two directions. So this events thing is actually an acceptor resource. And you can think out of it as a flow of incoming connections. And each connection, again, is two flows, one for incoming data, one for outgoing data. I won't show the full example here. It's, if you're interested, this is one of the examples actually in CAF. But the nice thing is the Flow API that I have showed you earlier is actually being used for WebSockets and allows you to very easily feed incoming data into a data pipeline and then process it along the way with whatever you want to do on the WebSocket frames. Deterministic testing. I'm almost done, promised, like 5 to 10 more minutes. Paiute, one of the original authors of the actor model, said at one point, one actor is no actor, actors come in systems. And of course, he was very right. But this also means if you want to test the system, then you have to test the actors, right? And you want to test the actors either individually, which means you want to very tightly control the inputs and verify that it sends the right outputs, or you have a collaboration between multiple actors, and then you have some kind of protocol between the actors that you want to test. And you want to test this protocol like in a very deterministic and step-by-step way. And in CAF, we have a testing DSL that allows you to test actors in a fully deterministic setup. We have this ping actor that we want to test. It has a pong actor as an argument and some integer, and it will send a ping to the pong actor and wait for the pong. And it will basically keep this ping pong loop until the value reaches 1. And the pong actor is just waiting for ping, and it returns pong with the value that it has received. And if we want to test this, we can use the CAF test framework with this particular fixture, which allows you to say, now I want to have my pong actor and a ping actor. You spawn pong first because ping needs to handle to pong. And then you can test the communication between ping and pong. So the first message is that you expect a ping message with an integer as second parameter. And this with is optional, but if you add it, you can basically look inside the message that is being sent. And in this case, ping atom is just an empty struct, so we don't care about the value. We can just say ignore. But we do care about the integer. And we want this integer to be 3 because we have spawned the ping actor with the value 3. And then we say from ping to pong. And then we check the back, the pong message that goes back from pong to ping. And then this continues for the value 2 and for the value 1. And at the very end, we want to say that the mail count is 1. And this fixture has this function mail count on it, which basically tells you how many systems are currently in total in your system. So it basically looks at all of the mailboxes and counts all of the mails up. And this is basically saying there is no other message at this point in time. And then this thing has implemented the protocol correctly. The last feature I want to mention is CAF also comes with an API for metrics. So if you have used Prometheus in the past, you should be familiar with counters, gauges, and histograms. In CAF, there are actually 2 versions of each, one with integer, one with double. The difference is integers are slightly more efficient because if you have a counter with an integer, it's a single atomic operation. It's just an atomic increment. If you have a double, you have to do compare and swap, so it's a bit more expensive. But if you have a double, and if you need a double, just use it. It's fine. And in CAF, there is this metrics registry where you can register, counter, gauge, and histogram families, or you can just create metrics on the fly that you want to use. And there is built-in export to Prometheus. So if you can either tell CAF via configuration with this configuration parameter, CAF middleman Prometheus HTTP, and you give it a port, and this will allow Prometheus to scrape the metrics from CAF. And there's also a built-in route that you can add to your custom HTTP server if you prefer to have one HTTP server doing everything. All right, that was quite a lot of stuff. So I hope CAF sounds interesting to you. And the last part is just a couple more slides to tell you, where do I start? Where can I look at? And the obvious thing, or the most convenient place to start at, is just to clone the GitHub repository. As I mentioned, CAF is BSD licensed, so all of the sources are available online. You can just clone it, build it. It's a CMake-based project, so you can use your usual CMake setup and build the thing. And if you have built the thing, play around with the examples. We have examples on a lot of topics, from low-level stuff like message passing to HTTP and WebSocket. And the snippets that I showed you earlier are actually examples in the repository, so you can just play with these things. And of course, we have a manual. You can bookmark it so that you can always have it available if you want to look, for example, into the CAF-net module, which has all of the HTTP, WebSocket, even if you want to do like low-level stuff directly on top of TCP, there's a lot of built-in primitives that you can use. We also have articles that go into much more detail than the manual. So the manual is more like mentions stuff and is a good place to find features. And then we have these articles that really go deep into certain topics, and they are hosted on Interance. So you can go to interance.io/learning, and there are a couple of article series. For example, we have a 2-part article series on implementing actors, which also tells a bit about best practices and why things are implemented the way they are. And we also have currently one example application on the website. We are looking to add more, but what we currently have is an example that simulates a warehouse backend. So you have a database you talk to, and you have a REST interface, and you can even do commands directly on TCP. It's just line separated JSON. And if you're interested, it's all available online. And we are always grateful for feedback on the articles and topic suggestions. So if there's something that you think is missing, please tell us. And you can find the community of CAF. We have a chat room. You can find us on Mastodon, Twitter. You can join our mailing list. And if you are a professional user, you can find us at Interance.io. We offer support contracts, workshops, training, architecture reviews, what have you. And if you are using CAF professionally and something that is actually in production, please consider signing up a support contract, because you don't want to get a support contract if you already need it, because then it's going to take a couple of days. Maybe your guy that can sign new contracts is away for a week, and then you don't have support if you need it. And of course, support contracts also allow us to pay the people that are working on CAF. And with that, I say thank you for listening. 8 minutes over time, sorry.
No, that's fine. And if you have any questions, I have a mic here because we're recording that. So just raise your hand. I'll come.
Hello, could you please go to one of the first slides where you have a big rectangle with drawings of messages, lambdas, and so on?
One of the first, so message passing?
Yeah, it was a slide, like third or fourth slide. Yeah, further. Yeah, back. A little bit back. Yes.
This one.
Yeah, Looking at this picture, I have an impression that actor looks like a class with methods, but later in slides, it appears that actor framework kind of avoids object-oriented approach specifically.
I
Because
wouldn't say avoid. It's basically a choice that you have. So this style of programming, if you just have a function, basically allows you, if you don't care much about state, then you can just write a function and avoid the extra overhead. But usually, if you look at actual C++ code, sorry, if you look at actual CAF applications, most of the time you will have classes with state and use this make behavior function as an entry point.
Yeah, but looking inside this function, it returns, let's say, something that is later is feed to behavior constructor.
Yep.
And it's the same lambdas. I mean, if you look at lambda, it's always this.
Yep. But you could also do something like std bind and give it a member function.
Yes, it makes sense.
It's basically a matter of choice. So in CAF, we do have a rather functional style. But if you prefer just member functions, then you can use std bind and pass in the member functions and use it that way. This works out well.
Okay, in this presentation, so there was only one example of main, and I wonder how you control how many threads the system is using, how many, well, which actor runs on which thread, or can you please elaborate on this?
Sure. CAF will start a thread pool in the beginning, and there are configuration parameters that allow you to fine-tune how many threads CAF is allowed to spawn for you, and you can also like fine-tune the scheduler. And by default, it will just look at how many cores you have and use that as a guideline. So for example, if you have like 20 cores, you will, I think, yeah, something around 20 threads. But of course, you can tell it to use less or to use more. And CAF will attach actors to whatever thread is currently available. You can detach certain actors. So for example, if you have an actor that reads to a database and you want to make sure that this is always on one thread because it does some blocking operation, for example, you can say CAF, please run this actor on one thread, and then CAF will basically assign one dedicated thread to this actor. Yeah. Yeah, this is what detach will do. It will attach one thread to this actor, and it will only run on that thread.
My question is, does it rely on, does CAF rely on RTTI and exceptions, or it can be built without RTTI and exceptions?
You can actually turn off exceptions in CAF. Yeah.
At RTTI?
RTTI.
Runtime type.
Yeah. We don't have a CMake option for RTTI. I'm not sure if it would.
If you don't use dynamic casts inside the library,
Yeah.
I guess you can.
I would have to look if it's possible. But there is a CMake option to turn off exceptions, and you can build CAF entirely without exceptions if you want it.
Thank you.
So on this slide, CAF put atom and CAF get atom, you said that it's like a text to tell framework what is the purpose of this. But generally, these tags used within a next layer of abstraction, right? Because CAF framework is the lowest level of abstraction. It provides building blocks. Cell state is a higher level of abstraction. It provides some business logic, right? And then we have a highest level, which is a client. And on following slide, I guess you have a get atom v tag. So how exactly client can get knowledge about what actor implementation provides to not looking into deeply inside of headers or implementation?
These atoms, they are just called atom by convenience, by convention. There's a macro in Kef that is called add atom, and it will basically just create an empty struct, and it will create a constant called whatever you name give it, _v, to have like an instance of this thing. But if we go to the client, this is what you meant, right? This atom view. So this put atom is declared somewhere. You could also just do kef put atom curly braces. It would be the same thing. It's just a matter of paste, I guess. So it's a type that has to be defined somewhere. So usually, so this put atom is actually defined in Kef. We have like a handful of atoms in Kef that are very common. So like put, get, delete, all of this stuff, but you don't have to use it. You can just declare your own message types. If you don't like this kind of style, then of course you can also make a message type that is named put, and then it has a member with the value. It's convenient to use these put atoms because you have to write less boilerplate code. But if you want to, you can just make one message type for each individual thing that happens in your system. Put atom is more like a, yeah, how should I put it? It's a bit inspired by Erlang, where you have these atoms with backticks that you can just use as metadata. So this is where it comes from. And it's basically just a convenient way to avoid having to write a lot of message types. But not to the implementation. It has to know about the put atom type because it has to send it something. So you have to have access to the types that you want to send to the cell, but you don't have to know about the implementation. And in the type version here, so here, usually what you can do is you can have this trait and then your typed actor in a header, and then everything else, so the cell state class itself, you can hide away in some implementation file and just have a function that creates this for you. And then you can, of course, do all of the hiding that you want.
Okay, more questions?
Can Kev log complete thing or scenario and replay it?
Log?
Log.
Log. Yes, Kafka has logging.
And
I didn't
can
mention it.
replay the log file?
You mean like as messages?
Yes, as messages. So
No.
instead.
So there's a logging API, and Kev can write log files for you, but this is more for something that you could feed into some log backend or just log files for debugging or to understand what a system is doing for something, for someone that runs the system. But it's not meant as a debugging tool in the sense that you record and replay.
Yeah.
Yeah, thanks. So I understand there's a thread pool for the scheduling of the message processing. I was wondering, this scheduling, can it take into account how much processing resources, time and memory each message would take or each queue would take? And is there some way to influence this scheduling?
You can tune a couple of scheduling parameters, but there's no way for Kev to know ahead of time how much time something would take to compute. So, but you can also, so for example, if you have an actor that receives a lot of messages, then there's a parameter in CAF that allows you to limit how many messages an actor can consume before CAF allows other actors to run. So this is something that you can tune, but not at the level of like knowing that this thing will take 1 millisecond or whatever.
A question regarding the spawning remote agents. So how does it know what to spawn? So the binary that runs remotely should have this type compiled in? Or what?
You mean the handle type?
Oh, I mean, you said that you can spawn agents remotely.
Yes.
And I mean, how does it know what type of agent? And
Yes. You have to register actor types at the configuration class, and there you have to give it a name basically. And
string
then,
name.
yeah, and then you spawn it via this common name, and you can give additional arguments to construct the other vector.
Okay. One question regarding flows. Is it possible to do flows that do branching somewhere in the middle, so that, for instance, image captured from the camera travels through the pipeline, and at some point it goes to different handling processes?
Yes, you can create streams. They're called connectives, and you can basically say a flow that you wait, for example, for two clients to come in before actually producing results. And then you can give the handle to 2 actors and they subscribe, and only on the second subscription you start emitting the data. So you can basically fork. You can also merge. You can also do things like zipping. So if you have multiple input flows and you want to process them in lockstep, so take one of the first, one of the second, one of the third, you can also zip things and do all of the branching that you want.
CD map, which is the open CD metric, and I probably don't want to.
If you use CAF, if you use CAF only for concurrency, you can basically cheat. There's a macro in CAF, allow unsafe message type. And this is you promising CAF that you will not send this over a network. And you better keep your promise, but then you can just use any type and don't write an inspect function for it. And basically allows you to do something that only works on a single machine. But you can get out of it, yes.
I have also a question about serialization. So
Yep.
Do you understand that the client and the server, they must be built with the same like binary, or like how do you ensure that the serialized type is safely can be deserialized on the receiving side?
Yes, great question. The answer is depends on the format. So let me find it. So you are writing this inspect function, and say you are serializing to JSON, then basically each field becomes just a key value pair. So if you have a new point 4D, which has an additional parameter, then of course you wouldn't understand the 4th parameter, but as long as you have X, Y, and Z, you can still serialize the 3 points that you care about. So you can basically have a sort of schema evolution in this way. But usually with the remote module, and I think this is what you're asking about, currently they have to be compatible in the sense that you have to have the same definition on all machines. But this is something that we want to address in the future. Right now, you cannot change the format that CAF speaks on the wire. And the current format is binary. So it expects like that XYZ is actually just 3 integers in real world, and then comes the next data. So if you do distributed actors with the current network I/O module, you have to have very much the same definition and the same types, yes. But this is something that we are already looking at and allowing you to do something else. And if you exchange a different format, for example, something like message pack, that would give you more flexibility.
Is it possible to integrate some custom serialization? For example, if I want to integrate with protobuf and all protobuf messages are inherited from some base class, so it's probably doable to figure out that this message is derived from this protobuf class, so I can use protobuf serialization and all the way back. And so
you can write your custom inspector, but currently you cannot exchange the default inspector for the remote module. But this is something that we want to address in future versions.
Sorry, one more question about serialization.
Yep.
So is when you do the inspection, do I have a correct assumption that you assign some sort of integer, like to identify the message by type? And how do you make sure that even, let's say, the definition did not change and the fields are in the same correct order, but that a different version of application compiled in a different order will not reshuffle the message IDs and that you will not execute it somehow wrongly, like you will not interpret the sequence in different way?
If you want to send stuff over the wire, you have to give each type a type ID in CAF, and these IDs won't change. So you have like a header, and then you list all of your types, and CAF will assign type IDs starting at some well-known type ID. So this will make sure that you always have the same type ID for the same type. And of course, it still means that you basically have to have the same header for all of your parts that you are building. You give it like a starting point. There's a constant CAF first custom type ID, I believe. And then you have a block of type IDs. And you just list your types one by one. And it starts by the first ID and just increments one by one.
Okay, let's maybe take one more last question, if any, and then we can go to private discussions.
Hello, thank you for the presentation. What C++ version the framework requires? Like 2017?
17 at the moment.
Yeah, and maybe like a follow-up question. Are you excited of some modern C++ features like concepts or state execution or reflection? Like what are you mostly excited about that you will use maybe in your framework?
I would love to start using concepts right away. Because in CAF, there's a lot of templates, and there's a lot of templates that are basically simulating concepts at the moment. So that's something I would love to clean up in hopefully not too far away future. Yep. One likely error, so for example, if you're using typed actors and you have the wrong signature in one of your lambda expressions, then CAF will basically give you the index of the handler that was wrong. So you at least probably don't get the exact source location, but at least CAF will tell you index 3, for example, has the wrong type, and then you can go through your types. But I mean, we tried our best, but you will probably find some place where we could do better, as it always is with templates.
Okay, with that, let's maybe just go to private chats, whatever. If you still want to ask our fantastic speaker something, I think he's still not running away from
Yes.
us. So, but first, let's say thank you very much for this nice presentation.
Thank you for coming.
Yeah, and thank you for coming.